In this video, we're going to take a look at hierarchical clustering as part of our study in unsupervised learning. So this will fit well with k-means, which we'll talk about in a separate video. But we know that we like to cluster because it puts groups of records together, which makes it easier for supervised learning because we can assess supervised learning on each cluster separately and maybe find some more accurate results. And we know that we see examples of clustering in many places, like the Linnaeus categorization of plants and animals, the periodic table of the elements, and market segmentation. So in this video, we're going to focus on hierarchical clustering, which is where we take a look at dividing up records into groups of clusters. And a dendrogram is a way that we can view these results and we can see how the data gets clustered. Now, there are two types of hierarchical clustering. One is agglomerative, which is where we start with two or more clusters and we merge similar clusters until a single cluster remains. That's what we'll see in a dendrogram, where we can watch each element as a separate cluster and then they merge and merge and merge until they become one cluster. And then we can simply draw a line to say this is where we want our optimal number of clusters. And then the divisive approach is to start with one cluster and simply break it down into multiple clusters, one at a time until we get that optimal number of clusters. So we're going to take a look at Ohio counties. We're going to look at election data, but we're going to strip out the election data. We're just looking at basically 6 columns that describe each county so that we can group each county appropriately. Now we'll take a look at a distance measurement, and we'll refer to this as Dij, where D is the distance between records I and J. And I and J are a vector of measurements. Now, the properties required for these measurements: first, non-negative assumes that each distance we're using positive numbers, not like negative to indicate backwards. Self-proximity means that the distance from an item to itself is 0, so it takes up effectively 0 space. Symmetry means that the distance from I to J is the same as the distance from J to I. And triangle inequality means that the distance between any pair cannot exceed the sum of distances between the two other pairs, or whatever that means. Now, the most common distance that we'll use is Euclidean distance, which is where we take a distance measure from I to J, we square it, we sum it with any other distance measurement used the same way, and then we take the square root of that entire sum. It's kind of analogous to the Pythagorean theorem where the hypotenuse squared equals the height squared plus the side squared. And then you'll often take the square root of that whole unit. So think of it that way, if that helps. So a couple distances we want to think about. If we're thinking about a cluster will have multiple members to it, and each of those will have a certain location. So minimum distance is the distance between the nearest members of two different clusters. Maximum distance is the distance between two furthest members of two different clusters. So we could say the distance from Ohio to Kentucky, if it were max, would be the distance from Cleveland to Paducah. On the other hand, if it were min, it would be Cincinnati to Newport, right across the river. Now, average is looking at the average distance of each item. So that one's a little trickier because we're looking at basically where the averages line up. And then centroid distance is probably the most common. With centroid distance, we're measuring the centroid of each of the clusters, and then we're measuring the distance between centroids. And centroid is effectively the average of all points put together. That would be the centroid of that cluster. So several different measurements that we can use for that. So let's take a look in a Python notebook. I start with several of the imports that we're going to need to use. And now I say PD set option display max rows none. That will show me all the rows from the data frame instead of truncating and showing me only the top 5 or the bottom 5. That'll be helpful here as we look at 88 Ohio counties. 88 is a nice bite-sized list we can look at, and we can scroll up and down. Now I pull in the Ohio election results, and here again you see we're going to have about 88 rows here, one for each county, and we're going to have the state, which we know the state's going to be Ohio for this, the county, several election results, but that's not really what we're interested in. We're interested more in these things like household income and unemployment. So first thing I'm going to do is set the index to county from the current numeric item, and then I'm going to grab a subset of only the feature columns I'm interested in. So we'll have a much more concise data frame to deal with. So total population, age 65 and over, median household income, unemployment percent, less than high school percent, less than college percent, and rural percent. Next, let's go ahead and compute distances. So this is going to show us the Euclidean distance between each county, and we can kind of start to get an idea of how we would cluster counties together. Those that don't have a far distance would likely be clustered together. Those that are further away would likely be in a different cluster. Now you see that computing the distances here is really easy in Python because we just use this pairwise.pairwise distances function, and we tell it which metric we want to use, which here we've said Euclidean. Remember, that's distance squared plus distance squared plus distance squared, and then the square root of that entire unit. And then we print that out in a data frame. Well, okay. I see things, a lot of these have an exponential value to them, and I realize that, you know what, if I'm going to compute distances, I really should normalize first. And remember what normalize means is we take the mean of each column, we take each individual value and subtract that mean. And what that does is that resets the mean to 0. Then we divide by standard deviation. So now the number that results is going to be a number where the mean of a whole unit is 0, and we're looking at standard deviations from the mean. So this will put our metrics on the same scale in case we have things of very different scale, like total population, which could be hundreds of thousands, versus unemployed percent, which could be maybe 16 or something like that. So we scale them, and then we'll go ahead and compute distances again, and we will see there's a bit of a difference in the distance computation. For example, let's take Allen and Ashtabula County. You see that's 7.04, but times 10 to the 3. Now, if we go down here and look at Allen and Ashtabula again, we see that it's 1.52 without any exponent. So the normalization is going to give us a bit of a different distance, and in our case, a bit of a better difference. Now, if we look at these, we can start to look for some outliers. And we can kind of just scan the numbers here, and luckily a lot of these are whole numbers without exponent. If we get down to Holmes County, notice that this is really an outlier compared to our other counties. If we look at the distance, we often see a whole number that's like 8, so a fairly significant distance. And we know that this is what we would call an outlier, and sometimes we're tempted to throw away outliers, but other times we're tempted to look closer at outliers and see if there's a reason why it is an outlier. So what I'm going to do here is look at only median household income and less than high school percent, and take a look at Holmes County compared to all the other counties in Ohio. And we see once again a significant distance compared to our other distance metrics. Now, I've lived in Ohio all my life, and when I put this together, like a data scientist, I was looking at the data trying to see what conclusions I could draw from it. And when I saw Holmes County, I thought, what makes Holmes County so different? What makes it so special? So I did a quick Google search, and I found Holmes County Amish Country Byway and then visit Amish Country. Okay, I see. Well, it ends up that Holmes County has a population greater than 50% that's Amish. And many times in the Amish community, they tend to pass down trades from generation to generation, like woodworking, farming, and things like that. And oftentimes do that themselves without engaging the public school system. And so that would explain why Holmes County has such a low high school graduation rate, which put it way out from the other counties in Ohio. And sure enough, as we do some grouping and clustering, we'll see that Holmes oftentimes is out on its own. When we do k-means clustering, it'll be interesting to see where Holmes County gets grouped. So that's why it's really interesting to do a bit of this distance matrix so that we can take a look at these special cases and decide how to handle them. And that's a quick look at hierarchical clustering. We'll continue this discussion with agglomerative clustering in our next video. I look forward to seeing you then. Thank you.